Welcome to the Chapter 2, Part 8 notes video. This is the last video from Chapter 2. So we're wrapping up the chapter, we'll have a review day, and then we will have the test. Our last section is about solving inequalities in one variable. So we've been looking at equations. We looked at polynomials, we looked at power and monomial functions, we looked at rational functions. The very end of this lesson, we will see one radical function, just because it's the exact same way of solving inequalities. So I'm going to start introducing that here. Our topics for today are polynomial inequalities, rational inequalities, and the final one is other inequalities and applying them. Why is this important? Because designing containers as well as other types of applications often requires solving an inequality. So for polynomial inequalities, we're looking at solving them just like an equation, except instead of equaling 0, now we're going to look at if it is bigger or greater than 0, so if it's positive, if it's greater than or equal to 0, less than or equal to 0. We're also going to look at when it cannot equal 0. Okay, the fundamental connection between inequalities and the positive or negative sign of corresponding expression for f of x. If f of x is greater than 0, means that we're finding all of the x's that will make y, or f of x, positive. So what that looks like is if we have a graph. So if I'm looking at something like this, what we've been doing so far is we've been looking at this function and finding the zeros, or the x-intercepts. Now what we're going to look at is for f of x being greater than 0, that means our y values must be positive, right? So that's these sections here where our y values, or our function values, are above the x-axis. And then we'll also look at when f of x is negative, or when our y values are below the x-axis. So this is where f of x would be negative or less than 0. The red would be f of x equal to 0. And the blue would be our function values, or our y values, greater than 0. Okay, so let's see if we can apply this. In this example, we have a function. This is a polynomial. It doesn't have a denominator, so this is a polynomial. And we want to know the real values of x that cause f of x to be 0, positive, and negative. Those are our only options. In this case, we're not looking at anything undefined because it's a polynomial, so we know that it's continuous over the entire domain. So let's start off with looking at when will it equal 0. F of x will equal 0 when x plus 3 times x minus 4 squared equals 0. The zero factor property says that this is when x plus 3 is 0, or when x is negative 3. And then also when x minus 4 is 0, or when x is 4. And we can say that this happens with a multiplicity of 2. Okay, so what does this mean? Well, I can sketch this graph. The degree here is 1 plus 2. Degree is 3. So that means I'm doing something with end behavior going up to the right and down to the left. When x is negative 3, we have an odd multiplicity, so it goes through that point at negative 3. And when x is positive 4, it goes back and bounces off. So this is the shape of our function. And then we want to know, when will it be positive? So I used blue for that. I'll use blue again. It will be positive between negative 3 and 4, and also greater than 4. So we can say f of x will be positive when x is between negative 3 and 4, and also when x is greater than 4. Notice I'm not putting or equals to, because if it equals to, then it would be 0. It would not be positive. 0 does not count as a positive number. 0 is neither positive nor negative. And then finally, we have, we're going to come back to the notation on that in a second, but f of x being negative is this kind of everything to the left of negative 3. So that means x would have to be less than negative 3. So notation-wise, if we're writing this in set notation, we would use these intervals. So we would say the set of x where inequality. X is between 3 and or -3 and 4. Also, x is greater than 4 or 4 is less than x, same thing. Or more often, we'll write this in interval notation. So interval notation means I'm saying all of the values between -3 and 4, almost like an ordered pair, but also everything from 4 to infinity. Okay, notice these are rounded, these are parentheses, these are not square brackets because we are not including -3. At -3, our f of x value is not greater than 0, it's not positive, it equals 0. And then the same thing for negative. If we're looking at set notation, this would be x, where x is less than -3. More often, we'll use interval notation. Interval notation says everything from -infinity to -3. This is not from -3 to -infinity. If we're using -infinity, we always do our intervals from smallest to biggest, from left to right. So -infinity comes first. Okay. For our equals 0, we have it here. We should write it in set notation. There's not really interval notation when it's just a value. So -3 and 4. There's no way to write that in interval notation for this class. There is a way to write it, but it's complicated and weird. Okay. Let's take a look at another example. So in our next example, we're looking at this inequality. We want to solve it graphically. And I've said, don't find the exact values, round to 2 decimal places is needed. Now, I'm looking at this and I say, how do I solve this, right? Well, recognizing this as polynomial on the right and a polynomial on the left, right? If I could get all of that over to one side, I would have a polynomial inequality. So let's write it as x cubed minus 6x squared plus 8x minus 2 is less than or equal to 0. So what I did is I just subtracted over the two terms from the right and I move them over to the left. So now I have f of x as x cubed minus 6x squared plus 8x minus 2. Every time I rest my hand on the iPad, it does weird things with the ink. Okay, so we're solving f of x less than or equal to 0. So how do we solve this? Well, we need to graph x cubed minus 6x squared plus 8x minus 2. Well, it's an x cubed. It doesn't look like I can factor, and it says don't find exact values. So in this case, I'm not asking you to find the exact values of these. We can use our calculator. So let's go ahead and pull up the calculator. All right, so we have our function here. This is f of x. Let's start by graphing it zoom standard. And this is a cubic function, so that's what I'm expecting it to look like. We do need to find our zeros in order to do this calculation, to see when it's positive or negative. So in order to calculate a 0, we're going to go second, calculate, option 2. Left bound, that works, so I'll hit enter. Right bound, I want to go to the right of the 0. I'm calculating this one that's on the left here. So enter, enter. The 0 is at 0.32. It's at 2 decimal places, right? Then we're going to do it again. Second, calculate, 0. Something on the left, something on the right, and enter. My second 0 is 1.46. The instruction said 2 decimal places, so I'm only rounding to 2 decimal places. And then my last 0 is over here between 4 and 5. So let's do second, calculate, option 2. My left bound is 4. My right bound is 5. Guess. So that is 4.21. Okay, so I have 0.32, 1.46, and 4.21. And when I'm looking at this, notice it is negative. If I were to draw this kind of as a chart, 0.32, 1.46, 4.21, this is negative, this is positive, this was negative, positive, negative, positive, right? This is what the graph looks like. It's negative, goes positive, goes negative, goes positive. That's just looking at the y values. Now we call this a sign chart, and we'll see in the next example why that's helpful. As opposed to having to graph it on a calculator every time, sign charts can save you a little bit of that computational work. So let's look back at our screen. Okay, so we had our sign chart. Zero 0.32, 1.46, 4.21, and our graph looked something like this. So as a sign chart, 0.32, 1.46, 4.21. Our y values are negative, positive, negative, positive. And we wanted to know when f of x is less than or equal to 0. So this means that we're looking at negative and 0. So if we're looking at our intervals here from negative infinity, we're negative. So starting at negative infinity, we satisfy the negative condition all the way up to 0.32. But this time we're going to include it because now we are including our zeros, union. Our next interval is positive, so we don't want to include that. But we do want to include 1.46 all the way up to 4.21, also including that endpoint. And our last interval is positive. We don't need that. So our answer here, these are all of the x values that would give us the inequality stated originally as a true statement. So we first set it as a polynomial inequality. We put the whole polynomial on one side, and then we graphed that and said, okay, where are the values, the y values, the function values? Where are they above the x-axis versus below the x-axis? Okay, let's look at our next example. Our next example is a rational function. Well, let me try clearing those another way. Okay, so we have a rational function here. We need to create and interpret a sign chart. So remember, a sign chart is what we were just looking at. When we looked at the graph, we could turn it into a sign chart. Now, hopefully, we can go from a function to a sign chart without the graph. So this is like a kind of a shortcut for graphing. When I don't need to see the whole graph, I just need to know the positive and negatives. So I'm going to start out with my axes. So here is x equals 0. Okay, and that's just going to help transition us from graphing to sign charts. The first thing I'm going to look at is my denominator. X cannot be 2/5. So here at 2/5, I'm going to put a dashed line, 2/5. X cannot equal 2/5. That would make it undefined. Okay, next I'm going to make our other critical values, which are our zeros. X equals 3 and x equals 5. Sorry, that should be a -3. So here I have x equals -3 and x equals 5. Okay, now this is going to turn into our sign chart. So what I'm looking at is my critical values, which are 2/5, -3, and 5. These are where x does something weird, right? Where our x value makes our whole function equal to 0 or a whole function undefined. Essentially, when is it 0 in the numerator or the denominator? And the reason this is important is because that's where it could change from positive to negative. Okay, so notice 0 is not one of our critical values. I put it there to help us visualize how a sign chart comes from the graph, but 0 is not one of our critical values. So I'm going to go ahead and copy my sign chart without the 0. 0 is not, I should say x equals 0 is not a critical value. So my critical values, sorry, I'm in the habit of doing this. Our critical values are -3, 2/5, and 5. And in between these critical values, we need to know, is it going to be positive or negative? So let's test our first critical interval, a number less than -3. So if I pick a number less than -3, let's just choose -4. -4 plus 3 gives me -1. I'm just going to write the negative because all I need to know is if the answer is going to be positive or negative. And then we have -4 minus 5, that's negative. So far, our answer is going to be positive. Divided by 5 times -4 is -20, minus 2, also negative. So our answer here will be negative. Next, let's test our next interval. Our next interval is between -3 and 2/5. Well, I know a number in there that I would love to test. Let's test x equals 0. 0 plus 3 is positive. 0 minus 5 is negative. 0 minus 2, whoops, I said negative and I wrote 5. 0 minus 2 is negative. Negative divided by negative is positive. So our next interval here will be positive. Next, we're going to test a number between 2/5 and 5. 1 is in there. 1 is a nice number to test. So I'm just picking a number, but I'm picking a number that's going to be easy to substitute into my function. 1 plus 3 is positive. 1 minus 5 is negative. Divided by 1 times 5 is 5 minus 2 is positive. So this is negative. And lastly, a number bigger than 5. Let's just choose 6. As long as you're choosing a number somewhere in that interval, you should end up with the same answer, positive or negative wise. So 6, 10, 100, you could choose. Okay, so x equals 6. 6 plus 3 is positive. 6 minus 5 is positive. Divided by 30 minus 2 is positive. This answer is positive. Okay, so what does this mean? Well, it means that my graph is going to do something. Remember, this was an asymptote, like this. Okay, now I happen to also know that the horizontal asymptote is actually an oblique or a slant asymptote. So this is something the question is not asking, but I'm going to tie this into something we've done previously, which is the slant asymptotes. The slant asymptote on this function, if I do polynomial division, will be x. Maybe plus or minus something, but it'll be kind of a slanted line. And so I know that this is going out along that line. Just some extra information that we can get from this function. Okay, so creating and interpreting, we created the sign chart. To interpret it, we can say that between -infinity to -3, x will be negative, or f of x, I should say, will be negative. I'm going to write it up here. between negative infinity to negative 3, f of x, is negative between negative 3 and 2/5, f of x is positive. Between 2/5 and 5, f of x is negative. And between 5 and infinity, f of x is positive. And lastly, f of x is 0 at negative 3 and 5. And we can say f of x is undefined for 2/5. So that's an interpretation. Okay, now, can't we just see that from a graph? Sure, we can see parts of that from a graph. But the interpretation part, the being able to look at the graph and telling me how that relates to our inequality, that's the new part for this section. Okay. Let's take a look at our last example here, and it has a radical. So we haven't seen square roots before. What are we going to do with that? Well, again, I can look at what would make this 0 and what would make it undefined, and then make a sign chart without even knowing what the graph looks like. So here I'm going to say x equals 2 is a 0, x equals negative 1 is a 0. So f of x equals 0 when x is 2 and negative 1. So those are our critical values. What would make this undefined? Well, x cannot be less than negative 1, right? X plus 1 has to be positive. Okay, so sign chart. Negative 1 and 2, those are our critical values. When x is less than negative 1, this is undefined. I can't take the square root if x is less than negative 1. For example, if x is negative 2, negative 2 minus 2 is negative. The square root of negative 2 minus 1 is negative. That is what makes this undefined. Okay, our next interval that we'd like to test is between negative 1 and 2. So let's pick 0. Whenever you can, pick 0 in your interval. Unless it is an x-intercept, it's a good number to test. 0 minus 2 is negative. Square root, 0 plus 1 is positive. Square root of a positive number will always be positive. So we have a negative times a positive, which gives us negative. And lastly, a number greater than 2. Let's pick 5. Again, dealer's choice. You can pick a different number than 5. 5 minus 2 will be positive. No matter what number you pick, it should be positive. Square root of 5 plus 1 will be positive. Positive times positive is positive. So what does this graph look like? Well, somehow it crosses the axis at this point, right? Oh, come on. So if I'm looking, here's negative 1, here's 2. It goes from negative to positive, and it stays positive, right? And somehow ends at negative 1, and it doesn't go any further, okay? So I don't know necessarily from this the shape of the graph. It could be just going up this way. It could be doing something like this, right? It doesn't tell me what's called the concavature. It doesn't tell me whether it's increasing or decreasing between those points, or if the slope is increasing or decreasing, or anything like that. All it tells me is when the graph will be positive or negative. In this case, in case you're curious, the graph actually looks like this kind of shape. Okay, but again, that's not what the question is asking. The question is asking, when will this f of x be less than or equal to 0? When will it be negative? So the answer is this green interval here. That's the only place that it was negative. And we also want to know when it equals 0. So our answer will be f of x is less than or equal to 0 for x values from and including -1 to 2. In a set, that would be x, where -1 is less than or equal to x is less than or equal to 2. X is between -1 and 2. Okay, that's it for this section. It requires a lot of understanding of everything we've done up to so far. So if there's something that's stumping you, make sure you go back and look at the sections where we looked at it before, or send me an email. Even better, set up office hours so that we can go through it together. And I'll see you in class.